today we have Laurent series. Let me first state it in precise manner. But it says that if you have annular domains, or let me take an annular region found with two concentric circles, let this bigger circle be circle C1, and they are concentric, they have the common center, and the smaller circle be C2. Both have the direction anti-clockwise, uh, and you suppose you have an analytic function in this annular region between these two concentric circles, and suppose that you have these circle C1 and C2. Suppose that F is analytic on the region dz naught. I will tell you what is this R2 union these circles C1 union C2. This is analytic function. F is analytic function on this region, and this region includes that this function is analytic on the circle C1 as well as on circle C2. And also let me write the radius of circle C1 be R1 and radius of circle C2 be R2. That is radius be R2. Where this region, this set is the annular region. It consists of all those points Z in C which lie between these two concentric circles. So that means it has to be R2 less than mod Z minus Z naught less than R1. This is the annulus, and this function is analytic on this annulus, including on this boundary. These circles C1 and C2 are its boundaries. Then F has an expansion of this form. Then for any Z inside this annulus R1, R2, you have F given by this expansion summation n from 0 to infinity a n z minus z naught to power n. So this is what we did in Taylor's series, but there you had the function to be analytic inside the disk. You don't have here the disk. You do not have the guarantee that this function is analytic inside the circle C2 as well. You just know that it is analytic outside circle C2 and inside circle C1, and between whatever region is between the circle outside of the circle C2 and between C1. So this makes here to get another additional part of this series, and this part of the series, it starts from 1 to infinity, and you may notice here you will have negative powers here. It is z minus z naught to power, it has to be, let me write it, how should I write it, as n minus 1. No, I should write it in a much different way. Let me write it. But anyways, it's okay. We do not have any problem in writing it. This is still good. Z minus Z naught to power n. So this is the called Laurent series of this function f when you have function analytic in a circle in this annular region. And let me give some more details about this. In this part, we have this one. This is obviously when once you write fz to be equal to this sum of these two series, these two infinite series, and that means both these infinite series are convergent. But let us look at the first part. The first part, this is also a power series, and it is convergent once you assume the Laurent series theorem. This is convergent, and you know what is power series. Once it is convergent at a certain point, it is convergent at this z, then it has to be convergent inside every point. Whatever circle you draw passing through z, it has to be convergent everywhere inside this circle also. That means this part of this power series represents a function, some function g of z, let it be. It represents a function, and you know that for power function represented by a power series has to be analytic. This function is analytic inside the circle C1. It has no problem anywhere in the circle C1. And this part is also known as analytic part of F. This is known as analytic part of F. This is known as analytic part of F. And look at this now, the second part of this series. The second part of the series. Here you can see you have a trouble at Z naught. This obviously this series is not convergent at Z naught, and we will be doing some result. We will be after this, maybe we will talk about power series expansion about infinity. So this is also a kind of power series, but here you have the powers of z minus z naught negative. If you take it to the numerator, then the power becomes minus of n, and this is the part that is to be studied further, that will be looked on further, where function fails to be analytic. By the time it seems that this function is not analytic at z naught, this part will be referred as a principal part. And this is a function, also it represents a sum function, it is a sum function, and this function is also analytic, but this is not analytic inside the circle C2, it is analytic outside circle C2. It is analytic outside circle C2, whereas this GZ, it is analytic inside C1. So in this way, what this Laurent series is giving you, that if whenever you have a function which is analytic on an annulus, then you can decompose this function into two functions, where these two functions, how they behave. This GZ is analytic. This is analytic uh, for this circle C1, and inside circle C1, that is the circle that will be this region R1, and this HZ is analytic uh, outside outside this circle C2, that is analytic for mod Z minus Z naught greater than R2. So this is a kind of decomposition. Whenever you have a function, you can decompose it in terms of two functions, and you know what is the nature of these functions. This decomposition we will be proving later on. Such a decomposition of this function is unique up to maybe adding constant, but with that will be verified later. So the first thing that now we have to write down the proof of this theorem, that this was just a remark to this theorem, that this thing, something like this follows from this theorem. We will be giving other remarks, but first let us focus on the proof of the theorem. Let us focus on proof of theorem. So what situation you have? We have this situation here. I have a circle C1. I have another circle C2. Both are concentric circles, This bigger circle has radius r1 and this smaller circle has radius r2, and obviously it is clear that r1 is bigger than r2. Now we have to prove that for any fixed z in this annular region, this function can have this kind of expansion. So let us fix some point here z in this annulus. Here we have z. So since this annulus is a domain, it is an open, so I can draw some disk around this also. Let this be, and the boundary of this circle, which is boundary of this disk is a circle, let it be K. And note that orientation is positive. Every orientation is, direction of each of these circles is in counterclockwise direction. Now, fix Z, Z in this annular region, Z0, R1, R2. Then look at this function now. This function f zeta over zeta minus z is analytic on D. What I am denoting by D? I am denoting by D this annular region D Z0 R1 R2, and now since I am having the denominator zeta minus z, and I'm taking out this some part around this z, and the part that I'm taking out is I'm punching out this disk, this pink disk from here. This is dz of certain radius. Suppose it has radius t. Some disk. I'm punching out it. So this is now a new domain. It has two kind of holes. So this function is analytic on this domain, and it is not analytic only on this domain. It is analytic on this, and it is also analytic on the boundary of this domain. Because by hypothesis this function f is analytic on the circle C1 and C2, and circle C1 and C2 is a part of the boundary of this D. It is C1 union C2, but you have another part of the boundary now. You have this circle K also. This is also boundary. So you have an analytic function, this f zeta upon zeta minus z on this domain D, and it is now this domain D is a multiple connected domain. It is not a simply connected; it is a multiply connected domain, and on its boundary has three components. But what I'm going to use now is that the Cauchy's theorem, Cauchy-Korsakoff theorem for multi-connected domains, which can be applied because you have this function. This is analytic function on this multiply connected domain and on its boundary as well. So by Cauchy's theorem or by Cauchy-Korsakoff theorem, you have that integral of this function f of zeta upon zeta minus z. Note that z is fixed now over the boundary of D. It has to be 0. But now let us look at this boundary. This boundary has three components, and once you look at the integral, your orientation is decided in such a way that when you are traveling on the boundary, your domain must lie to the left of yourself. That side, that direction is considered as a positive direction. So that means now, according to this convention, C1 is in positive direction, whereas C2 and this K are in negative direction. And when something is in negative direction, when you have to break down this integral, it has to be written as C1 minus, it has to be C2 because C2 is in negative direction, and it has to be K, and you are doing f of zeta upon zeta minus z d zeta. This is equal to 0. Now you further simplify this. What you simplify, according to my requirement, I am taking this integral over k to one side, f zeta upon zeta minus z d zeta is equal to integral over c. It is f of zeta upon zeta minus z d of zeta minus, it is c1, and it is minus c2 f of zeta upon zeta minus z d zeta. Okay, right hand side I will keep. I have to do lot of work with this, but let us look at this now on the left hand side. This left hand side is the integral of the function f over this circle k, and integral f, not no, I'm not looking at this f upon zeta minus z. I'm just looking at f. This f is analytic on this k, and it is analytic inside k also, because the whole f is analytic in this annulus, and this k and its interior is a part of this annulus. So I can use there the Cauchy integral formula, and by Cauchy integral formula, value of f at z is nothing but this thing. So by Cauchy integral formula, I get this thing to be f of z is equal to, but in case of f of z, you have 2 pi also, 1 upon 2 pi. So I have to write 1 upon 2 pi I here, 2 pi integral. This is c times f of zeta upon zeta minus z d zeta minus integral over c2 f of zeta upon zeta minus z d zeta. Let us keep this as equation 1. Now we will repeat uh, something that we did with Taylor's theorem here. Now I have to expand these terms, 1 upon z minus zeta and minus 1 upon zeta minus z. Now I can write this 1 upon zeta minus z as no, but I have to be precise for where zeta I am considering. I am considering, when I am considering zeta on a bigger circle. Now for zeta in the circle C1, this is the circle C1, and this is a smaller circle. Now you have zeta somewhere here on the bigger circle, and you have z here, and this is the center. Okay. So this is some distance of z from z naught. Let this distance be r. Distance of z from z naught. Let this distance be r. Okay. And other distances, we know what are other distances. Now for the zeta in this, I can write this number as 1 upon zeta minus z by adding z naught and subtracting z naught, and take out, let us first write that zeta minus plus, I can write z minus z naught. Sorry, I have to write it minus z minus z naught. And now what you're going to do, you just bring out this zeta minus z naught, and that will give you 1 upon zeta minus z naught, and then you are left with 1 over 1 minus z minus z naught upon zeta minus z naught. Now you expand this through geometric series, this 1 upon 1 minus c, where c is now this ratio z minus z naught and zeta minus z naught. And what you will get, you will have this thing 1 plus c, where c is z minus z naught upon zeta minus z naught, plus so on z minus z naught upon zeta minus z naught whole power n minus 1, plus you have this z minus z naught upon zeta minus z naught whole power n upon 1 minus 1 z minus z naught upon zeta minus z naught. Okay, this is it. Now you just multiply both sides by f. So you get f of zeta upon zeta minus z naught. You have this zeta minus z naught and no, sorry, this is zeta minus z. This is not z naught. So this comes out to be equal to, on the right hand side at the same time you have to multiply each term in the numerator denominator by zeta minus z naught also. So the first thing that you will have is f of zeta upon zeta minus z naught plus it will be z minus z naught into f of zeta, our you will have denominator zeta minus z naught square, zeta minus z naught square. Plus if you look at the other term you will have z minus z naught square, but I'm just writing not mentioning it here. It will be z minus z naught to power n minus 1 into f of zeta upon zeta minus z naught to power n, and the last term is again here I have to be very particular what it will be. It will be z minus z naught to power n, and then I will have f of zeta, and in numerator I will have zeta minus z, because if you take the LCM and your LCM will be zeta minus z naught, and you will have then cross multiplication zeta minus z naught minus z minus z naught, and minus minus will be plus, z naught will be cancelled out, you will be having zeta minus z into, you will have from numerator you will have zeta minus z naught to power n, but that will be cancelled out with zeta minus z naught, but at the same time it will be back multiplied with zeta minus z naught, so will you have power n of zeta minus z naught here. Okay, this is the expression. Now the next step is to integrate this expression over c. And if you integrate it over c, you will have this integrate c1, because you are considering that you have this c1, and this will be our integral c1, because z minus z naught can sit outside. This will be integral over c1, and this will be integral over c1, and also you just multiply it with 1 upon 2 pi I also, 2 pi I, 1 upon 2 pi I throughout, you multiply it by 2 pi I also. Just it became 2 close upon 2 pi I. So you have this expression now, and let me now give some names to these expressions. So now I can call this expression first to be a naught, and I can call the second expression to be a2, a1, and so on up to a n minus 1. And the last expression, last term here will be denoted by r and z. So this I am writing as a naught plus a1z plus, sorry, it is not a1z only, it is, just a minute, I can, it is a1 z minus z naught plus it will be then a2 z minus z naught square plus so on, it is a n minus 1 z minus z naught to power n minus 1, and I have an error term which I am denoting by r n of zeta. Okay, where note that these a's are nothing but these are 1 upon 2 pi I over c1, integral over c1 f of zeta over zeta minus z. It is zeta minus z, yeah, it is zeta minus z naught, zeta minus z naught to power n plus 1. Zeta minus z naught to power n minus 1 d of zeta. This is so far whatever n you take 0, 1, 2. So these are the notations that I gave to these terms that came there in my expression. And now let us look at this where this and r and z. What is r and zeta? R and zeta is z minus z naught to power n upon 2 pi I integral over c1, and it is f of zeta upon zeta minus z into zeta minus z naught to power n into d zeta. This is the expression. So with the first integral, we just wrote this thing and let it be equation second. Now regarding the second integral in this expression here, regarding this integral, let us make some more. Also it has 2 pi I with it, 1 upon 2 pi I. So now let us differentiate it, let us expand it in a bit different way, because now you have, in the earlier case, zeta was on the circle this and z was inside the circle this. Now in the next case, in the second integral, you have zeta coming from this inner circle here and z is lying outside this circle. So then next regarding the for the second integral in equation first, I hope I have given it name 1. Take cancel. Yeah, I have given it name first. So in the second integral, I can write this minus. I have minus also there, zeta minus z, as I have to make some quick change here. What I'm going to do, I'm going to absorb this minus also, and then I'm going to write it as z minus z naught minus zeta minus z naught. Now it is the same thing that you had there. And now you just take out now this z minus z naught and then expand whatever is left to you through geometric series. What is left to you is 1 minus zeta minus z naught upon z minus z naught, and let us expand this through geometric series, geometric progression. It will be zeta, it will be 1 plus zeta minus z naught upon z minus z naught plus it will be zeta minus z naught over z minus z naught square plus so on. You will have zeta minus z naught upon z minus z naught power n minus 1, and the last term as usual has to be zeta minus z naught upon z minus z naught power n upon 1 minus c, whatever c is this, zeta minus z naught upon z minus z. And then you multiply it with f of zeta and integrate our circle C2, and also multiply throughout by 1 upon 2 pi I. You will have this expression, which implies that 1 upon 2 pi I minus integral over C to f of zeta d of zeta. Sorry, it should not come be in the, it is zeta minus z, d zeta. Now on the right hand side, what you will have, look here, on the right hand side you will have, also note that z minus z naught is being multiplied. That means in throughout, the power of z minus z naught will be raised by 1, and in the last expression you will have zeta minus z naught upon, if you compute the numerator, in numerator you will have z minus z naught minus zeta plus z naught. Z naught will be cancelled, it will be z minus zeta, and the power of z minus z naught will be n, because z minus z naught is multiplied from outside also. So it is now 1 upon 2 pi I integral over f of zeta d zeta upon but I oh sorry okay, let me write it 1 upon z minus z naught. I can write separately this z minus z naught. It has nothing to do with the integral. Plus second term is 1 upon z minus z naught square integral 1 upon 2 pi I. You have this uh, f of zeta, and now here look, what you will have, you are taking out this z minus z naught. From here you are taking it out as a power 2, because another term is from out coming from outside. But now zeta minus z naught is in numerator. Here you have zeta minus z naught being multiplied with it into d zeta, plus so on. You will have the last term where you will have power of z minus z naught to power n into 1 upon 2 pi I. It is integral over c. We are taking integral of c2. It is c2, and you will have f of zeta, and see what will be the power of zeta minus z naught now. In the power this you have zeta minus z naught power n minus 1. It is n minus 1 d zeta. It is n minus 1 d zeta, and the last expression, whatever it is, let me denote it by qn of zeta, and qn of zeta, and qn of zeta is something when multiplied. Okay, let me write what is this qn zeta, where qn of zeta is equal to now 1 upon 2 pi I. At the same time I have z minus z naught to power n, and what else do I have? I have z minus z naught to power n, and I have zeta minus z naught to power n being multiplied with f of zeta and then integrated. I have then integrated c1 is f of zeta. It is zeta minus z naught to power n d of zeta. So this is q. What do you call it? Is q at z. Now look at this. What we have now. What form of q we have now? But I have another expression also in numerator also. I have no in numerator also z minus zeta also. It comes from here. Look at this expression here. You will have z minus zeta also left there, so it has to be with it. So this is it. Or finally, what you can do? Finally, I can write this 1 upon minus 1 upon 2 pi I integral over c1 f of zeta over zeta minus z naught, zeta minus z, and d zeta as, I can write it as b1 plus b1 upon z minus z naught, plus it was b2 upon z minus z naught square, plus so on, plus it is b n minus 1 upon z minus z naught to power n minus 1, plus you have qn of zeta. Let this equation be 3. Yeah, this is it. What exactly is it? Now, but this is the power. Oh, here you have this. What should be the power of this? Okay, let me see. Okay, this has to be n. Okay, no problem. No. I just got mixed up with some things. I should have power. This is n. Just a minute. Just a minute. Mm. Okay, and then let me write this not b, and let me write this to be b and because power is now, you don't have power n minus 1 and q and z, where these coefficients b n are these numbers 1 upon 2 pi I integral f of zeta. I'm writing it in a different way now. This is zeta minus z naught to power minus n plus 1 d zeta. You can check this. Our integral c1. Look at you. So you suppose n equals to 1. For n equals to 1, you will have b1, and b1 will be the value because minus 1 and 1 will be 0 power. You will be having only integral 1 upon 2 pi I ci over c1 f of zeta d zeta. This is what this integral is there. The first integral. Look at this. This is b1. Let me write in a different color this to you. Now let me write it in some good color. Okay. This is b1. This is b1, and then this is b2. Here you have zeta minus z naught, but this zeta minus z naught is same as to write 1 upon zeta minus z naught to power minus 2 plus 1. You don't have any problem. This is again same. This is the way I'm writing. So this is, and then this expression is b of n, and here you have zeta minus z naught to power n minus 1, and if you write it in another way, another way you can write this expression as zeta minus z naught minus n plus 1. This is what it is. So you have these all settings where qn's and rn's exist. Now, what I'm going to now try to do, I'm going to prove that these error terms Qn and Rnz goes to 0. This Rn zeta and Q and zeta, they both tend to 0 as n tends to infinity. First, look at this Rn zeta. It is kind of repetition what we did with Taylor's theorem. So first, let us look at the modulus of this Rn of zeta. This has to be equal to, it is z minus z naught to power n upon 2 pi I. I have taken the modulus integral over c2 f of zeta upon, what is this? Let me try to look at the expression for Rn. Yeah, this is the expression 2 pi I zeta minus z into zeta minus z naught to power n. Okay. So this is zeta minus z into zeta minus z naught to power n into d zeta. You make certain adjustments. You have z minus z naught, distance of z from z naught is r. So, but okay, let me write first. This had to be mod of z minus z naught to power n upon 2 pi. Modulus of I will be 1. Integral c2 is mod of f of zeta upon mod of zeta minus z naught power n mod of d zeta. Now again, f being an analytic function on C2, so it is continuous over C2, and C2 is a compact set, so this function has a maximum there. So I'm going to denote the maximum of this function. Let capital M be the maximum of this f of zeta over this curve C2. And this is always finite because of compactness and continuity argument. And then also note that this zeta minus z, it can be written as zeta minus z naught plus z minus z naught. Sorry, this is minus. This is minus here. Okay, here, this is minus here by triangle inequality, And what is this zeta minus z naught? Zeta is coming from now circle C2, and the distance, the radius of the circle C2 is R1, and the distance of z from z naught is R, and this is always positive, and its reciprocal will be less than or equal to 1 upon R1 minus R. And so now substituting these expressions in this above inequality, again you will have a finer estimate for this modulus of Rnz, size of Rn, this error term. You will have less than or equal to, I can replace this now, mod of fz with its maximum, and I'm going to replace this mod of z minus z naught to power n with r to power n. Zeta minus z, reciprocal of zeta minus z is b, will be replaced reciprocal of 1 upon r1 minus r, and zeta minus z naught, this is the distance of zeta from z naught, which is the radius of the circle c. And then the other thing that will be left to you is the, okay, let me not skip all the steps. I will be having m maximum, and then I will be having r to power n. I have 2 pi, and then I have 1 upon r1 minus r into r1 to power n integral our C1 mod of d zeta, and this is the arc length of this circle C1, which is actually 2 pi r1, and this is equal to further m. I'm writing this r separately, r1 minus r, and I'm writing r upon r1 to power n minus 1. Rest 2 pi I gets cancelled, because this expression, this thing is equal to 2 pi r1, and also r1 will be reduced by power 1, so that's why I have kept the power of r1 to be n minus 1 also. And now since you have this r is strictly less than r1, so this r to r1 is less than 1, and if it is less than 1, then the corresponding sequence goes to 0, converges to 0 as n goes to infinity. So what it means, if that means this whole thing goes to 0 as n goes to infinity. That is, this error term, its modulus goes to 0 as n goes to infinity, whatever zeta you take on the circle C2. Okay, this is done now. What it means then, this implies that that this integral now 1 upon 2 pi I integral over C1 f of zeta upon zeta minus z. This integral is equal to this power series a n z minus z naught to power n, where n is equal to 0 to infinity, because error term went to 0. So you just establish this integral. Also now let us look at the error term q n zeta. Next, let's look at this q n zeta, its estimate. It has to be equal to mod of, it is 1 upon 2 pi I into z minus z naught to power n, and it is integral over C2, and let me write to see what is this expression. It is what is q n. Okay. Yeah, this is q n, and 2 pi I z minus z naught power n c over integral C2. Sorry, this is integral C2. F of zeta minus z naught to power n upon z minus zeta. You have f of zeta minus z naught to power n upon z minus zeta d zeta. Now you use the strength of this modulus and the triangle inequality. For the integrals, you will have this thing is equal to 1 upon 2 pi, but I'm just taking this because the distance of z from z naught is r, so I'm writing directly this r to power n, which is mod z minus z naught integral C2 mod of f zeta. Also this now you have this zeta coming from the smaller circle C2, and the distance of zeta from z naught, which is the center of the circle, so to the radius r2. So it has to be r2 to the power n upon z minus zeta mod of d zeta. Okay, you have this expression. Again, f being analytic on this circle, so is continuous, so it will have its maximum, and let that maximum be small m. Maximum of this f of theta over the circle C2, and also note that z minus theta, I can write this. Now z is lying outside. I have z here, and the zeta is coming from inside the circle. So what I can write now, I can write it to be is greater than or equal to, it is z minus z naught minus zeta minus z naught by triangle inequality. This first term is bigger than the second term. And what is this? Z minus z naught is r, and this is r2. And obviously r is bigger than r2, so this is a positive number, and this reciprocal will be less than 1 upon r minus r2. Substitute these terms in this above inequality, you get further reduction in the size of this error term q, which is less than or equal to, you have a small m, it will be 2 pi r to power n times, you will have also you have also r2 to the power n upon r minus r2, and times you are left with this integral of mod of d zeta over c2, which is the perimeter, or what you say, the length of the circle. It is 2r. And now you see here, I will write here expressions only. You will have this number cancelled with 2 pi r, and now you will be left with m times, let me, you have r2 power, r2 to the power n plus 1, but let me keep r to the power separate here, and in numerator I am writing r minus r2, and then I have r2 upon r to the power n. And now here, look that this r2 is the radius of this smaller circle, and r is bigger than this. So r2 upon r is less than 1, and when you take its power, then that converges to 0 as n goes to infinity. As n goes to infinity, that means this qn zeta goes to 0 as n tends to infinity. Hence what you have then, hence you have this integral 1 upon minus 1 upon 2 pi I integral over c to f of zeta upon zeta minus z d zeta, converging to this series summation n from 1 to infinity b n upon z minus z naught to power, and this is what we had seen there in this expression. Okay, you just see here. So this is Rn. Where was this? Yeah. No. No. This is somewhere back. This is estimate. Yeah, here exactly. You have this integral equal to this, and once you prove that this qn goes to 0, then you will have this series. Now substitute these values in equation 1. What you get thus, first becomes, what was first? First was your f of z equals to, it was integral 1 upon 2 pi I integral c1 f of zeta minus z d zeta minus 1 upon 2 pi I integral over c2 f of zeta upon zeta minus z dz. You have the value for these integrals as power series, as the series expansion. So, and for the first integral, you have n equal to 0 to infinity. This is an, all the powers positive of z minus z naught. And in the second part, where you have n from 1 to infinity, it is bn upon z minus z naught to power n, and this is true for every z in this endless region, R1 and R2. This is the Laurent series expansion of this F set. So let me ask you: do you have any questions? Tell me, please. If you have any questions, बोलिए. Am I audible? Na?
Yes, sir. No, no question, sir.
Let me say me like marks please. So what are the remarks? This series is called Laurent series, and now here remarks. Now, what was the situation? You had this situation that function is analytic inside this annular region, and this is the circle C2. And now, if you have this situation that f is analytic inside circle C2 also, suppose uh, f is analytic inside C2 also, uh, except at z not only. It is analytic everywhere except at z not only. Then what you can do, then you can take this radius R2 to be arbitrarily smaller, because you know this it is analytic elsewhere except at Z2. Then R2 can be taken arbitrarily small, and then the Lorentz series for Fz valid in this region 0 less than mod z less than R1. उस वक्त R2 लेने की आपको जरूरत नहीं होती. You just have to avoid this. Sorry. It has to be z minus z dot. So it has to be 0 less than z minus z dot less than R1. It will be valid there. But further, if this function happens to be analytic even at z naught, then what happens? If f is analytic even at z naught, C2 के अंदर भी एनालिटिक और z naught पे भी एनालिटिक, then f of zeta upon zeta minus z naught to power minus n plus 1, which is actually f of zeta into zeta minus z naught to power n minus 1, are analytic functions, is analytic inside C2 also. क्योंकि ये पावर नेगेटिव होने की वजह से ये zeta minus n naught तो पॉलिनोमियल है, whatever power you take n equal to 1 2 up to for n equals to 1 2 so on up to, ये तो एनालिटिक फंक्शन C2 पे भी और C2 के अंदर भी ये एनालिटिक फंक्शंस हैं. तो ये एनालिटिक फंक्शंस हैं अगर, तो यू नो कि आपके पास सिंपल क्लोज कंटूर, अगर कोई फंक्शन एनालिटिक होता है तो उसका इंटीग्रल बाय कॉची-कोरसर थ्योरम 0 हो जाता है. तो इसका मतलब therefore by theorem Cauchy-Courset theorem, the integral of these functions f of theta over theta minus z naught power n minus n plus 1 d zeta will be 0 for all n equals to 1 2 so on. In particular अगर इसको मैं 1/2 pi I से मल्टीप्लाई करूँगा तो भी जीरो हो जाएगा. But what are these integrals? These integrals are nothing but these are the values of dn's. The coefficient dn's will be zero, and hence then the Laurent series of f is उस वक्त Laurent series of f क्योंकि b सारे जीरो होंगे तो it is this is nothing but this is only this part you have. But this is nothing but this is a Taylor series. Taylor series. That means Taylor series is a particular case of Laurent series. So Laurent series is a more generalization of Taylor series, you must say. So because we can reduce this Taylor series from Laurent series. Because in that part you have that in principal part all these coefficients will be zero, so that part will be zero. You will be having this only analytic part, and this is nothing but this is the Taylor series. बोलिए कोई दिक्कत इसमें?
No, sir.
Another thing, with the help of Cauchy-Gorsuch theorem, you can have another remark 3. See, you have this here. This is C1. You have this C2. And take another circle. Let me take another circle C between this and this. Now you have things since your functions since f zeta upon zeta minus z naught is analytic. This is analytic in this angular region T z naught R1, R2, and C1 union C2. तो हम what we had done एक रिजल्ट किया था कॉशी मल्टीपली कनेक्टेड रीजन कि जब डोमेन के ऊपर फंक्शन होता है तो उस डोमेन के ऊपर डोमेन की बाउंड्री या एक कंटूर के ऊपर आप फंक्शन एनालिटिक लेते हो तो इंटीग्रल का वैल्यू ओवर दिस बिगर कंटूर इज सेम एज द वैल्यू inside this smaller contour. So that means the value this 1/2 pi I integral over C1 f of zeta upon zeta minus z naught to power n plus 1 d zeta, because this is an analytic function, whatever power I take here n plus 1 also, this integral over C1 is same as the integral over C. इसका वैल्यू का कोई फर्क नहीं पड़ता है. Is same as f of zeta over zeta minus z naught to power n plus 1. Okay, and see, that means what was this integral? This integral is a coefficient an. और similarly आपके पास coefficients similarly bn के लिए भी आपके पास हो जाएगा. bn आपके पास आ जाएगा. You can change this path of integration because the value will remain same. You can take it over c f of zeta upon zeta minus z naught to power minus n plus 1. You have minus n means you have a negative n. What you can do, you can write it to be c minus n, where n is anything. You may write it as c minus n, and you may write this as cn also, no issue. Now, what you can, when you write c minus n, that means you are taking terms. So with this convention, you are fixing up any arbitrary contour inside the annulus. Coefficients ans and vns can be computed by integrating these particular functions, taking all the positive negative powers of zeta minus z naught, and hence the Laurent series then Laurent series of fz can be written as, now it can be written as f of z. Instead of writing two series, you just write n from minus infinity to infinity, anything. It is cn z minus z naught to power n. Now, if this it has all the parts, positive as well as negative parts, where Cn is what? Cn is your 1 upon 2 pi I integral over contour C, where C is arbitrary simple closed contour inside this annulus, f of zeta, zeta minus z naught to power n dz. This is the more general form, general form to write the Taylor series, Laurent series of n, such a function. So you have any questions now? Okay, let me